Excellent, ladies and gentlemen. All righty, take out your computers and get logged in because we're going to be working on a lab in just a minute. Holy cow. All right. Achilles. Joshua.
Yeah. I'm surprised.
Who am I missing?
Should you pass? Well,
All right, ladies and gentlemen. Okay, today we've got a lab that we're going to work on. Okay, now the lab requires a lot of technique, and it's probably like nothing you have ever done before. So I'm going to demonstrate the lab for you up here, but you need to pay close attention because of the fact that, again, you're probably not going to ever do a lab like this ever again or ever before. But our question of the day is this: how can you collect and measure an amount of gas produced in an experiment? What's the problem when you produce a gas in an experiment? It escapes. Where does it go?
It just spreads here into the room.
Goes into the room. How can we prevent that from happening? Okay, we have to trap it in something, right? But to trap it in something, we would have to do the reaction in something. And then how would we measure a gas? I mean, gases do what? What's the unique thing about gases? A solid, we could find its what? Mass. Put it on balance, find its mass. What's the problem with a gas?
You can't do that.
Why? You're absolutely correct, and you said it before. Where does the gas end up?
In the room.
In the room, in the air. Okay? Well, if we create a gas, we don't want it mixed in with all the other gases in the air. So today we are going to collect the gas, and we are going to measure it. Now, the only way that we can collect and measure it, ladies and gentlemen, is to do what is called collecting it over water. So we are going to bubble a gas through water and collect it. Because a gas will, what we call, displace water. Gas is created, it will force water out of the container it's in, and it will take its place. The problem would be if I were to do an experiment at the bottom of this container and it produced a gas, what would happen?
It would bubble.
Okay, and where would the bubbles end up? And then off into the air. So what's the only way I could trap that gas? What would I have to do to this container?
Cover it.
I could put something on top to cover it. Absolutely correct. I don't have anything big enough to cover this. Or the other thing I could do to the container is what? Well, if I have the container like this, where's the gas end up? Come on, you just said it 3 minutes ago. What? It ends up in the air. What if I do it like this?
It'll get trapped in the dome part.
It'll get trapped in the dome part. This is actually a gas collecting tube, ladies and gentlemen. It's marked with measurements. What do you notice about the measurements on here, Stephen? Where are the lower numbers?
At the top.
Lower numbers are at the top. Larger numbers are at the bottom. This is a gas collecting tube. Now, I don't know what's so exciting, Caden, but really right now you don't actually need your computers. Okay? So,
Nothing's exciting.
what?
Nothing's exciting. I don't know what you're saying.
It had a lot more of your attention than I did, sir. Okay? So we're going to use these to collect and measure the gas because they are marked off in milliliters. The same thing a graduated cylinder will be marked off in. The difference is 0 is up at the top here and 50 is down at the bottom here. So as we put a gas in here and we collect it, we're going to be able to measure the volume of it. Okay? Now, what things do we need to know about a gas if we are collecting it? Think of ideal gas law. What are some things that we need to know? We need to know a volume. Easy enough. Here's our container. It measures volume. What else do we need to know? Pressure. How are we going to measure pressure? Good question, huh? What else do we need to measure? Temperature. How could we measure temperature? Thermometer. Thermometer. Now let me ask you this too. If we collect the gas through water, what temperature do you think the gas will be at?
Or the water temperature?
At the water temperature. Very good. And all our water right now is at
Room.
so that way when we're collecting it, we will have an idea of what temperature the gas will be. Okay? But we still need a pressure. Right? How can we find the pressure?
The thing we did that one time with the syringe.
There you go, ladies and gentlemen. We got a gas pressure sensor. What's it reading right now? What's it hooked up to?
It looks like the stapler, but I don't know.
Well, no, this end. What's it hooked up to on this end? Because that was the end we attached the syringe to. What's it hooked up to?
Nothing.
So what's it reading?
Nothing.
Nope. Still reading something.
The air.
Room gas.
It's reading the air pressure pushing onto the inside of the sensor.
Yeah.
So we can actually measure that. Okay? Now, here's the one problem. And this is a problem that we've never had to face before. But if you take and bubble a gas through water, okay, some of the water will evaporate, which then makes it a what?
Phase change.
Okay, good. What state?
Like
If it evaporates, what state will it be in?
gas.
Gas. Gas. So in our container, we will not only have the gas from the experiment, but we will also have a gas from
Water.
water. But we don't want to know how much water we're collecting. We want to know how much gas from the experiment we're collecting. So that creates a challenge for us today too, and we're going to show you how to handle that throughout the lab today. Okay? So ladies and gentlemen, what I need you to do is I need you to open your computers to the gas law lab. Okay? The one that looks like this, ladies and gentlemen. Okay? And let's talk about what we are going to be doing today. Josie's already going, you're not showing us anything. There you
I
go.
didn't say anything.
I could hear you screaming it in your mind.
Sure. I'll go back.
Okay. So, this is the purpose of our lab, to use ideal gas law to find the amount of moles of a gas produced during an experiment. Okay? That is what we are going to be doing. Okay? Now, what we're going to do is we're going to read through the experiment real quick, the procedure, and then I will go over and show you how to do it, and then you're going to go in back and you're going to do it with a partner. Okay? Too much work here to work alone. We do have an odd number of people here. That means we'll have one group of 3. But that's it, one group of 3, everybody else will be working with partners, okay? So here's what we're going to do. You are going to measure and record room temperature and room pressure. There are thermometers out at each station. I think we got an even number of people now. Hello, sir.
Hi.
Okay? So you're going to record room temperature and you're going to record air pressure. Okay? Now, actually, probably what would be better than room temperature would be to record the water temperature. They should be the same because the water has been sitting out here all day and since yesterday, ladies and gentlemen. So they should be the same. So your data is going to be recorded down here in this table, ladies and gentlemen. Okay? Room air pressure, mass of magnesium ribbon, temperature of water, volume of gas collected, partial pressure of water vapor. Well, we'll explain what that is. Okay? You're then going to get a piece of magnesium ribbon. At your station already, ladies and gentlemen, there are these pieces of magnesium ribbon that are cut up and waiting for you. Okay? Cut up and waiting for you. See, now I like Caden open his computer. Now he's staring at it again. You want to bet if I went on Senso, he wouldn't be on the lab? Okay? So, the problem is you need to take this magnesium ribbon and we need it to stay in the bottom of the container during the reaction. We don't want it to float up to the top because it will slow down the reaction. So we're going to fold the magnesium ribbon in half a couple times and we are going to make a copper cage out of copper wire. I know, I'll show you what that means. Okay? The cage should hold the magnesium ribbon in place, yet allow the hydrochloric acid to get to the ribbon to complete the reaction. Be sure you leave enough copper wire is left to hook it over the edge of the gas collecting tube. Again, I will show you what all that means because I know if you read that, I wouldn't understand a word of it either. Okay? Then you're going to get 20 milliliters of 6 molar hydrochloric acid. Now, you remember the hydrochloric acid we worked with in the last unit? The stuff that was really concentrated, the stuff that could burn your skin really bad? Good news, this is only half strength. Still strong enough to burn your skin, still strong enough to make you blind. Okay? So you need to be careful with it. You're going to get about 20 milliliters of 6 molar hydrochloric acid, and you're going to put it in a 50 milliliter beaker. All of these things are out at your lab station for you, ladies and gentlemen, including the 6 molar hydrochloric acid, which I will put my goggles on before handling, which is right here, ladies and gentlemen. If you drop this, it hits the table, it splashes up and gets on you, it will burn. So you need to use caution when you are using it, ladies and gentlemen. But because we need 20 milliliters of it, this is the only way I can do it. Why don't you take out your own computer, open it up, and get to the lab, please, sir? Okay, do that now. Okay?
What?
Well, I said do it now, and you're sitting there not doing a darn thing. After you put 20 milliliters of hydrochloric acid, and it's approximately 20 milliliters. It does not need to be exact. That's why we're using graduated cylinders, or I'm sorry, why we're using beakers for this. You're going to slowly fill the rest of the collecting tube with water. Now, where do you get the water from, ladies and gentlemen? You are going to get the water out of the bin of water that is at your station because we know the what of that water. We know the temperature of that water. Okay? Then you're going to lower the cage of the magnesium ribbon into the gas collecting tube and you're going to hook the wire over the edge. Set the wire by placing a one-hole stopper on the gas collecting tube. This is a one-hole stopper because it has one hole in it, which is good because then what can come out of the tube? No, the liquid, not the gas. We want to collect the gas. This will allow the liquid to escape. You're going to place your finger over the hole firmly. You are going to flip the gas collecting tube upside down, and you're going to lower it into a plastic tray that has been half filled with water, and then you are going to remove your finger after the stopper is below the water level in the tray. The reason that you are doing this, ladies and gentlemen, is if I fill this tube with water and turn it over, what will happen? The water will run out. However, if I fill this tube with water, and then I put a cork on it, and I put my finger over it, and now I put it under the level of the water, guess what? The water won't run out. Because the water in there will stop it from leaving. It will hold it in place. Until the gas starts filling up the top of this tube. and it will force some of the water out through the one-hole stopper. That's what we want to happen. Okay? So you have to hold this under the water the whole time the reaction is going. You have to hold this under the water until you get your final volume reading. We will show you how to do that, ladies and gentlemen. Okay? There is a trick to that. Only after you have gotten that final volume reading can you turn this back over, take the cork out, and dump this down the drain. Questions? Okay. The reaction is given by the following equation. We are going to take magnesium, react it with hydrochloric acid. We will create hydrogen gas and magnesium chloride. Which gas are we collecting? Gosh, I was hoping that wouldn't be the hard question. Really? Maybe there's only one gas in that whole equation. Bless you. Still? No one can find the gas? What?
The H, hydrogen?
Hydrogen gas. Good. It's right there. H2 gas. Hydrogen gas. Man, we're going to go back to naming later on. No, we're not. Okay? After the reaction is complete, ladies and gentlemen, wait a few minutes. Tap the glass collecting tube on the bottom of the tray. Why? Because if there are any bubbles clinging to the side, we tap it on the bottom so those bubbles get up where we can collect them. Okay? And now, here's the hard part. You're going to reach in and you're going to cover the hole again on the bottom of the container. You're then going to pick it up and you're going to bring it over to this graduated cylinder, and you are going to keep your finger on the bottom until you get it inside under the water again, because that will stop the water inside from doing what? Escaping. Now, is there any way for me to measure the pressure of the gas inside there? I can measure its volume. Is there any way for me to measure its pressure?
Probably
The little thingy over there. No, you don't have one. We only got one for the whole class.
We count it?
What?
Do we count it?
How?
If we know the temperature and volume.
Always no.
Yeah, but we don't know the number of moles.
Oh, that's wrong. Can we assume one?
No, you cannot.
So it's
You can't do that this time, because it does matter this time. What pressure do we know?
Room pressure.
Room pressure. We are going to do something called equalizing the pressure. We want the pressure inside the tube to be equal to the pressure outside. That happens, ladies and gentlemen, when the water level inside the tube is equal to the water level in this container. Watch the water level in this container, ladies and gentlemen. What has it just done?
I can't see.
Went up. Which way did it go? Watch the water level. You ready? As I pull this out, which way is it going?
Down.
If I push it in, it's going.
Up.
When I get to the point where the water level inside here and the water level here are equal, that will mean the pressure of the gas inside the tube and the pressure of gas outside the tube are what? Equal, and now we know the pressure. Now we know the pressure. Okay? So that is the last step that we have to do. And this is where you read the volume on here. Okay? Now again, when you're reading volume, there are markings on here for 10, 11, 12, 13. But there are also markings between 10 and 11, so you better figure out if those are tenths or not. Because you need to report your answer as accurately and as precisely as possible. After you get this volume, ladies and gentlemen, then you can take this tube, you can flip it over, you can take off your stopper, pull out your copper wire, and dump everything down the drain. Everything down the drain. Questions? Okay. So, Hang on 1 second here, ladies and gentlemen. I need to switch cameras. So, here we go, ladies and gentlemen. All right, I need someone to come up and give me a hand. Who's going to come up? Thank you. Good. Excellent. Who's going to come up?
Josie will.
Josie, grab your goggles on the way up, please.
Sir.
Okay. After you have found the mass of your magnesium ribbon, close your computers. I need your complete and undivided attention. Close them. After you have found... Pierce, close your computer. You're going to take your magnesium ribbon. You're going to fold it in half like this. Do not press it down. It will break in half. I want to fold it, but I don't want to press this edge. And then I'm going to fold it a second time gently so that it is folded over twice. Okay? Now I'm going to take this piece of copper wire and I'm going to put it through the magnesium and I'm going to wrap it around the magnesium in some way so that it is held in place. Just like that. All I've done is wrapped it around there. Okay? At this end, I'm going to take it, I'm going to make a little hook. A hook shape on it. This is now ready to go, but I've already found the mass of this. Questions? Okay. Josie, I need you to hold this upright for me like this, please. You're going to take and you're going to put 20 milliliters approximately of the hydrochloric acid into your beaker. And then I'm going to pour it into here. Let go, please. I'll get this. I'd rather spill it on me than on you.
Appreciate it.
Okay. Now, if I put in 20, what are we near there?
More 19 than 20.
That's close enough. You could also measure it on there. Can you hold that for me now? Now you take water out of your container and you finish filling this completely up. By completely, as high as it will go, actually letting it overflow at the top. Now I take my magnesium ribbon, which is in the cage. I put it in there, hooking it over the edge. Take my stopper, put my stopper on there. And now I take and I flip it over. Okay? That was, I think, all I needed you for, Josie. Thank you.
Sounds good.
Okay? Now, you need to make observations while this is going on. And you can't see it from there, but I can see a lot of stuff happening in there, including the magnesium starting to react with the hydrochloric acid. Okay? Now, this is going to take a few seconds, maybe a few minutes. I have no idea how Pierce is seeing any of this with his hood pulled down over his head. Pierce, how many fingers am I holding up? You sure? Okay, good. At least it wasn't one, Pierce. Now we see a lot of bubbling going on, ladies and gentlemen. Now that reaction is really taking off. At the top here, I'm starting to see the gas being collected. It's starting to make its way to the top. The water level is going down and down. We are actually collecting that gas. The problem is we're also collecting what gas? We're also collecting some water vapor. As these bubbles make its way through the water, some of the water naturally evaporates and becomes a gas. Now we'll talk about that in a minute, but now you can see I'm really starting to get a lot of gas collected, right? Okay? So we're going to go until all that magnesium ribbon is gone. The reaction will stop itself when we run out of magnesium ribbon. Okay? The reaction will stop itself. Okay, you're going to bring me your magnesium ribbon and I'm going to cut them to make them smaller. Otherwise, what just happened to me will be happening to you, which is what? No.
No, it's-
Long time?
What?
Take long.
There's nothing left in the tube. There's supposed to be some liquid left in the tube. I can't measure it. Too much gas was created.
Well.
But I can show you what we would still do, which is at this point, tap it. Get all the bubbles to the top. I'm going to put my finger over the bottom. I'm going to bring it over here. I'm going to hold my finger on the bottom until it's under the water. Then I can let go. And now, what? I told you, it pushed out all the water. There will be some left in your tube. There will be some left in your tube. And now I would take and I would move this up and down. As you do, once you get the water level inside the tube, even with the water level outside, you're then going to read the volume that it's at inside in that tube. So you may not want to turn your container so you're not looking through all these lines and things. The back side of it is clear. When you have it so that the water level inside the tube and in this container are at the same height, you read the volume on the gas collecting tube. Once you've got that, you're done. Okay, you are done. So we take this out. We take the cork off. We take the copper wire, set it on the counter, pour out the remaining water that is in there. Leave this sitting on the desk for the next class. Undo your copper cage as much as possible. And you're done. Now we got to do the numbers and the data and things. Now there is one other thing. We said we collected what with this? Water vapor. Now, here's the nice part about collecting water vapor, ladies and gentlemen. When you bubble a gas through water, the amount of water vapor that is created is directly dependent on the temperature of the water. Okay? The temperature of the water. So if we have a gas in a container, how does it create pressure?
by moving.
But-
Hitting the wall.
Hitting the walls of the container. So what would happen if I had one gas in there, hitting the walls of the container, and then added a different second gas? What would happen to the pressure? Increase. Why? Well, not necessarily double the bouncing, but there's a certain amount of bouncing from one gas
Yeah.
and an amount of bouncing from the other gas, correct? Okay? Luckily for us, ladies and gentlemen, because that is temperature dependent, we can figure out what the pressure, the water vapor, creates inside the container. So we had a total pressure. Ooh, look, a preview of what you're going to learn tomorrow. Inside the container that came from the pressure of what two things? What gases are inside there?
The water vapor. And then the hydrogen.
Which means that if each of those is bouncing on the wall some, that will give us the total pressure, right? So if I want the pressure of just the hydrogen gas, I need to know this, because I know what the total pressure is. It's going to be room pressure. I need to know what this is, ladies and gentlemen. For that, ladies and gentlemen, we have this wonderful table. This is the pressure of water vapor between the temperature of 15 and 38.8 degrees, or 30.8 degrees Celsius. Now, here's how you read this, ladies and gentlemen. First of all, this is in kPa. kPa. Why? Because in a minute I'm going to show you our gas pressure, and it's in kPa. So let's say you are at 20.4 degrees. Here's 20. Here's 0.4. This would be the pressure of the water vapor of the total pressure in the tube. So let's say, for example, the total pressure was 98.72 kPa. That's equal to the pressure of the water vapor plus the pressure of the hydrogen gas, correct? Okay? Well, we just said that at 20.4 degrees Celsius, which we can use to read this chart, we can't use it in our calculation, correct? Because we would need what unit for temperature? Kelvin. But for this chart, we can read it by using Celsius. It's 2.3957. kPa. So of this 98.72 kilopascals of pressure, this much comes from the water. What do we do to find the pressure of the hydrogen? We subtract them. So the pressure of the hydrogen is going to be equal to the total pressure minus the pressure of the water. You subtract them, and that will give you the pressure of your hydrogen gas that is inside there. Questions? Open your computer. Here's your first piece of data, ladies and gentlemen. There's the pressure in the room right now, 98.84. 98.84 kilopascals. We are a little below standard pressure in the room right now, because what would it be at standard pressure? Don't everybody jump on this one all at once. It's only kPAs.
101.3.
101.3. So, room pressure right now that we are all going to use for this experiment is 98.84 kPa. That is what we are going to use. So in the data table near the bottom, ladies and gentlemen, room air pressure 98.84 kPa. That is what you will put in there. Questions? All right, ladies and gentlemen. We're up to 20 people. That is 10 groups of 2. Everything is set out at the lab stations. If you want aprons, they're available in the back. Grab your goggles, grab your partner, and go get to work, ladies and gentlemen. Do not measure any magnesium until I come around and cut yours for you. Otherwise, it will be too much, and you will have to do the experiment all over again. Then you find a new partner. Let's go. Find oil. Well, are you going to do calculations in this lab? Yeah. I would probably bring a calculator.
Oh, you have to calculate it. Okay, it's just better anyways. I tend to make a lot of mistakes.
There you go. Who's your partner?
Oh, I crashed into a curve again. It was too much slow. I was crazy.
Yours is cut. Yours is ready to go. By the way, don't forget to make observations in every spot where it said to make observations, ladies and gentlemen. Look at the lab and see what you're supposed to be observing. Yes, you still have to fold it in half twice to make the cage around it. I just need to make it smaller for you, otherwise it's gonna be too big. You're not gonna be able to collect that amount of gas.
How are you guys?
MG River. Is this the MG River?
Can I have your magnesium ribbon real quick, please? Thank you very much.
All things look good, yeah.
Hopefully that'll work for you. There you go.
Mr. Brand, how do I make this little cage thing?
Well, first of all, you have to bend the magnesium ribbon in half twice, otherwise you can't make the cage around it. Dude, take your hood down because your goggles need to seal around your face, and they're right now sealing around your hood.
No way. Like so no.
You'll be okay.
Mr. Brand.
You will be okay.
Mr. Brand.
What?
I'm broken.
And you need to get a different piece.
Should I just leave it here?
What?
Should I put what should I put?
Let's put it back in the container. Sir,
Next time.
give me Joshua's goggles.
Maybe you'll do it.
They'll be yours. Then you're out of the lab. Get out. Give me 50 cents.
Oh, yeah.
Cut into my profit margin, dude. You don't just grab somebody else's goggles and use them. I've been telling you for days to bring your goggles.
Can't buy new one.
What?
Can't buy new
You
one.
can go down to the office and buy a new one. But right now you're renting a pair of mine for 50 cents. For what?
$1.
You betcha. I'll let you have 2 rentals.
Nah, it's not.
I'm getting out doing this. No, I'm scared.
This number. Okay. Please get it because then I'd like to talk about the questions. I hope, ladies and gentlemen, you left everything cleaned up. That your copper wire is sitting there right next to the cork so the next group can find it, that you kind of unwound the copper wire to be nice to the other person. Okay? I hope as Eric and Morgan are finding out, room temperature doesn't change, which it doesn't. That's the reason that yesterday I had all of these things sitting out there so that they could get used to or become room temperature. So that again, hopefully you don't forget things. Can I go off? Well, you guys are still needing to get your temperature, correct? Okay. Do you have it? Okay. So do you have the 2 numbers that you'll need? If not, you can come up and read it because I know this is difficult to read. Does that help? By the way, ladies and gentlemen, what can change during the day for this lab? The pressure. So please, if you have a friend who's in 3rd hour, don't think they're going to use 98.84. That may change by then. So if you're helping them or they're helping you and you're like, well, he didn't give us that number, please understand that that number can change. Okay? That number can change depending on the conditions outside, which make the pressure inside change as well, just so you know. Okay? Probably won't be too bad since it's 2nd and 3rd hour, But in the past, when I've had a class like first hour and fifth period, it sometimes changes quite a bit. Is there anyone who needs this table to get their last number anymore? Okay. Now, so here's the thing. You should have at least 3 observations of the magnesium ribbon. You should have done 3 observations of the hydrochloric acid. You should have done at least 3 observations of the reaction of the two. The room air pressure was 98.84. The mass of your magnesium ribbon was yours individually. No one else probably had that same number. The temperature of the water. Now again, we had 20.4 or 20.8 and 18.3. My guess is one of those thermometers isn't very good. I don't know which, but that would be my guess. But you have to go with the numbers you have. Okay? And then finally, ladies and gentlemen, you had the volume of the gas that you collected inside the tube when you equalized the two of them. And we had the partial pressure, which you just looked up on the table. Is there anyone who needs any of those numbers? Good, because I can't give them to you. Those are all individual. Every one of you is going to have different answers for this. Now, here is one thing that I want to show you, and this is a preview of what we're going to learn in the next unit, ladies and gentlemen. This is a balanced chemical equation. Okay? In this lab, what did we run out of in the reaction? The magnesium ribbon. Magnesium is what we call a limiting reactant. It's what we run out of. The reaction stops because there's no more magnesium. Okay? Now, in the next unit, we are going to be able to predict how much product is created by how much reactant we began with. Okay? That's where we're going. But we're going to make this simple. What is the coefficient, the big number in front of the magnesium in this balanced chemical equation? 1. What is the coefficient in front of the hydrogen? That means that they are in a 1-to-1 ratio. That means for every mole of magnesium that you had at the beginning, you should have created a mole of hydrogen gas. It's a 1-to-1 ratio. So however much magnesium you had at the start, that is how much hydrogen gas you should have created. Okay? How much you should have created. Now, when we come down here, assuming that all of the magnesium gets used up in the experiment, how many moles of hydrogen gas should have been produced? Take the mass of magnesium and convert it into moles. Take the mass, convert it into moles. That's how we know how much hydrogen gas should have been created. They should be equal. You need to show me your work, and you need to put it in that box. And you have done converting from grams to moles hundreds of times. I shouldn't have to tell you how to do it. Number 2, look at the bottom of your table up above. What is the value for the vapor pressure of water in this experiment? What was it? What was yours? Write it down in here. Here, I want you to show me how you found the pressure of just the hydrogen gas. I wish somebody would give you an example of how to do that so that you could do it. Okay? Kind of walk you through it, explaining to you that the total pressure that we had in the classroom, 98.84, had to be the pressure of the water vapor and the pressure of the hydrogen gas. And that if we subtracted those two, we would easily find the pressure of the hydrogen gas inside there. Somebody should do that so that you can find just the pressure of the hydrogen gas. Now, number 4 says knowing temperature, pressure, and volume, how many moles were created? What formula do we need to use? Anyone? I'll wait. What formula are we using in number 4?
Ideal.
That's one I would probably use. You could do it with combined gas laws. I would probably do it with ideal. But be careful. What's the one tricky thing there?
Is that R?
Nope. R's are constant. We know those. We're good with those, right, Phoebe? 8.31. What's the only tricky thing there? What do you use for pressure?
KPA?
Which one? We have 3. If you want the moles of hydrogen gas,
Just the hydrogen gas?
we better use the pressure of just the hydrogen gas. Just the hydrogen gas. The number that we calculated here. That's the one we better use. Otherwise, we're getting the pressure of the moles of hydrogen gas and of water. And of water. I will show you how to do percent air tomorrow, ladies and gentlemen. It is a calculation that we can do. Okay? It is a calculation that we can do. By the way, for these questions, for number 2, what is the total pressure of the gas collected in the tube? I do not want a number there. I want an explanation of what the total pressure is. I do not want a number there. Other than that, these should be fairly easy for you. Have a good day, ladies and gentlemen. Easy, taking out my computer there. Goodbye, goodbye, goodbye.